Let's take a look at the idea of drainage patterns now. Drainage patterns reflect local topography, the geology, especially things like faults, and climate. Channels occur in areas where surface runoff occurs, and materials can be loosened and transported by the kinetic energy of water. The classification systems tell us something about topographic and geologic controls that make water flow in different ways, and also that lead to erosion on a landscape. And much of what I'm going to talk about here is from a book called The Physical Environment, which is an introduction to physical geography by Michael Ritter, and there's the link below. Here are a few questions to think about as you watch this. How would you classify Hunter Creek? And can you think of an example for any of the other classes of the systems listed below, the drainage systems? Let's start with dendritic drainage. It's one that we think of most commonly, and it's most commonly used to illustrate what a watershed is. A dendritic drainage pattern is the most common form, and it looks like the branching pattern of tree roots or tree branches. It develops in areas that are underlain by a relatively homogeneous or material that's roughly the same throughout. Not a lot of resistant and unresistant rocks and things like that. So the subsurface geology has a similar resistance to weathering, so there's no apparent control over the direction the tributaries take. Tributaries joining larger streams, they join larger streams at acute angles, which means that that's at less than 90 degrees. And that's how you get the branching effect that we see that's so common in a lot of surface drainage systems, especially in the Sierras. Parallel drainage patterns, here illustrated by the little dots on the dotted lines on the map, are patterns that form where there's a pronounced slope to the land surface. So one where we would have a mountain face draining, say, for example, into a valley. The parallel pattern develops in regions of parallel, elongated landforms like outcropping resistant rock bands. Tributary streams tend to stretch out in a parallel fashion, following the slope of the surface. A parallel pattern sometimes indicates the presence of a major fault that cuts across an area of steeply folded bedrock. All forms of transitions can occur between parallel dendritic and trellis patterns, and we'll see the trellis. The trellis drainage idea is an interesting one. It's named after the the common garden trellis. This kind of drainage develops in folded topography like that found in the Appalachian Mountains of North America. There are these downturned folds called synclines that form valleys in which we find the main channel of a stream. Short tributary streams enter the main channel at sharp angles as they run down the sides of the parallel ridges called anticlines. Tributaries join the main stream at nearly right angles. The rectangular drainage pattern is found in regions that have undergone faulting. Streams follow the path of least resistance and are concentrated in places that are exposed to rock that's the weakest. The movement of the surface due to faulting offsets the direction of the stream, and as a result, tributary streams make sharp bends and enter the main stream at high angles. And this is an example of a drainage on the San Andreas Fault in California. Radial drainage develops around a central elevated point, for example here a mountaintop. This pattern is commonly found when you have conical shaped features such as volcanoes. The streams extend from the headward reaches upslope toward the top of the volcano. So we have the headwaters of several streams that originate near the top of the volcano and then join together as they reach the base of the volcano. And here's Mount Rainier as an example of that. Centripetal drainage. This is an example of a small playa that's between Empire and Nixon. And if you look carefully, you can see the evidence of drainage on both sides of the playa, draining directly into the playa itself. And here, this is the opposite of a radial drainage system, because the streams are flowing into a central depression. And this would be a very common drainage system in the state of Nevada, because all of our drainage actually flows into the state and none actually goes out of the state to the ocean. This is a pattern that's typical of the western and southwestern portions of the United States, where basins exhibit interior drainage. That is, that the drainage flows into these playas and never leaves, except by evaporation. In wetter times of the year, the streams feed small lakes that evaporate during dry periods, and these create these large, flat salt beds, sometimes these dry lake beds, that as the salt dissolved in the lake water precipitates out of solution and it stays behind as white evaporite. We have the deranged and contorted patterns. Here we have, these are developed from the disruption of pre-existing drainage patterns. And here, in this case, we see a dendritic pattern that was altered but then overrun by a glacier. And the glacier left behind a fine-grained material that forms wetlands and deposits that dam the stream to impound a small lake. Finally, the tributary streams appear significantly more contorted than they were prior to glaciation. And this is partly because, again, material has been deposited in a way that's very different, and it's altered the topography of the landscape, which also alters water flow patterns. So here are questions. How would you classify Hunter Creek? Well, let's take a look at Hunter Creek, and through the ArcGIS website, here's an image of it. This looks very much, we see the outlet for drainage up here in the northeastern corner. You can make out, though, when you look specifically at the map with using the ArcGIS tool, you can make out that the that the drainage pattern itself is very much the dendritic pattern. Finally, if you want to look for other classes of systems listed below, I suggested, or the systems that we looked at, I suggest first of all that you look at some of the playa drainage systems to look for some of the systems that are actually internal, draining internally. That would be, for example, a centripetal drainage system. If you're interested in a drainage system that is more of a radial drainage system, look on the flanks of Mount Lassen to see what the drainage patterns look like there. Mount Lassen is a fairly recent as the result of a fairly recent volcanic eruption, and you'll probably find a radial pattern in that kind of terrain.